Okay, what we're looking at here is the south tower of the World Trade Center, just as it's beginning to explode. The top part, the break is actually occurring up here where this black smoke is, and the top part of the building is actually starting to lean over, and the bottom part starts exploding down the side, well ahead of the actual collapse of the tower itself. I'm going to be recording the ejection velocities directly for two little plumes of material here that are going to be quite noticeable after a few frames here. The way I'm scaling this picture is I'm using these the girders along the side, and I looked it up, and these have a spacing of 1 meter. So just count the girders, and that's how many meters. Okay, so that gives a scale to the picture, which allows me to actually come up with measurements on these two sets of data. I've already plotted the data points, and if I step through it, you'll see, okay, there comes the top one, and there goes the bottom one right there. And notice they start off very quickly. Those are huge jumps at the beginning, and then they slow down, and then they mix with the rest of the material eventually. In any case, one thing that you might have noticed is every few steps there's a frame that's fixed, and this is because, I believe it's because of a change of frame rate at some stage in the processing of this video. I looked at several versions of this, and they all seem to have the same issue. So individual frames aren't going to be reliable as far as timing, but if you look at the average over several frames, we can get good measurements that way. I'm using 30 frames per second, and I'm just taking these every single frame because I'm looking at a fairly small time interval here. Okay, let's go ahead and analyze the data. I'm using, by the way, this software package is called Physics Toolkit, and it's commonly used by physics classes. Okay, we're looking at two objects, and the horizontal direction is the x direction. We're only going to look at that component of the motion, and we're going to plot position versus time. On a position versus time graph, the slope would indicate the velocity. Now this is the position for data set 1. I'm going to move this up so we can see the little readout at the bottom. Okay, notice down here it indicates in this little box the slope and then the uncertainty in terms of the scatter of the data. Okay, and here's the graph. Notice that it starts steep and then it sort of flattens out. So in other words, we're talking about a dust cloud as it's ejected at one speed, and then it sort of takes on a different speed later on, and it's a relatively smooth transition. Notice there are several places where there's pairs of data points that are pretty much identical positions, which would indicate one of those steps I was telling you about. So that gives you an idea of the, we can't just take individual, so the slope between here and here is not going to be relevant, but from here to here. But if I go over a number of frames, it should be still good. Okay, let's plot the slope. Actually, let's not do that. This is a second version of the graph, and this one is called displacement versus time. And the only difference is it puts a 0 mark on the first data point. And so we're able to spread out the data a little bit better and see what we're doing. So what I'm going to do is I'm going to look at this initial velocity. I'm going to take 4 data points just so that we have a good reading here. So if anything, the initial velocity could be a little bit higher because it should be steeper at the beginning and then taper off as we go with time. But I'm going to take the average for the first 4 data points. So we go from there to there, and notice it comes out the slope, which is the velocity of 44.98, so roughly 45 meters per second. Let's bring up a calculator. Okay, I've already programmed into the memory the conversion factor between meters per second and miles per hour. So let's type in 44.98. By the way, the minus sign just indicates these plumes are being shot to the left, which is normally the negative direction. Okay, so 44.98. So 44.98 times the conversion factor is 100.6. So it's roughly 100 miles per hour for that first plume. Okay. As time goes on, let's take the latter portion of this. If I go, like, say, from here to here, now it looks like the velocity of ejection is about 13 meters per second. I've seen this kind of numbers quoted before, and apparently they were looking at further out in the ejection like this. So if I take 13.17 times the conversion factor is 29 miles an hour. So basically we're looking at something starting off about 100 miles an hour, tapering down to about roughly 30 miles an hour after a few frames here. So in fact these are like tenths of a second, so from 0 to 2 tenths, 4 tenths, 6 tenths of a second here. So all of this is within that first second. Okay, let's go to the next one. Here's the second run, and notice that there was a delay before the actual ejection occurred. And again, let's look at the displacement graph. And again, this one looks a little bit jumpy, so we're not going to just look at, say, one particular transition there. So let's take the slope, say, from here down to, let's say, the first 5. That's the first 4. We'll take those first 4 data points there. Slope is 56.3, so that's 56.3 meters per second. 56.3 meters per second times the conversion factor equals 125 or 126 miles per hour. This one is even faster. Okay. Again, if I took the slope further on, like let's take it from here over to here, so the average of this part of the run, it's about 18 or 19 meters per second. Let's see what that is. Clear it. 18.56. 18.5. Let's put the full number in there. Times the conversion factor, about 41, 42 miles per hour. Okay, so as you'd expect, once a puff of material is blown into the air, it's going to have a lot of turbulence. It's going to slow down, and that's what we see. Notice overall, if we smooth out the little jumpiness here, we have sort of a transition. But this initial speed here is the speed that we're really interested in mostly. That's showing that material is being shot out from the side of the World Trade Center here at a point below where the actual collapse is occurring at over 100 miles an hour. Okay, this is the original clip from which the measurements were taken, and there's just one fraction of a second in there that you could see those 2 little plumes coming out.